Hi everyone, welcome back. We're going to start this video with another example of using the divergence theorem. So in this example, we want to find the flux of the vector field xyz across the cone, z equals the square root of x squared plus y squared, where z goes from 0 to 4, and the cone has a downward orientation. So to show you the situation here, here's our cone with a downward pointing normal, which would be an outward pointing normal, which is what we need for the divergence theorem. But here we can't use the divergence theorem. The reason is that we don't have a closed surface. This cone is just this lateral surface here. The top is completely open. So we're not allowed to use the divergence theorem. But we can get around this by closing the surface. So we can pretend that we're going to close this surface by putting a disk right here, or putting a top on this cone. And then if we put a top on that cone, then what we have is a closed surface, and we can use the divergence theorem. So that's exactly what we're going to do. But we have to be careful. So this shows you some flexibility when using this theorem. So now we're going to pretend that our surface S is really a combination of two surfaces, so it'll still be piecewise smooth. The first surface is going to be the cone, S1. We can parameterize that as u cosine v, u sine v u, because we know z is equal to the radius by the given formula here. And S2 is going to be the disk that's going to serve as the top of this cone to close it up. And the disk is just going to be u cosine v, u sine v, 4, because the z component of this disk is fixed. It's just flat. Okay, and we need to make sure that the normal vector for the disk points up so that we still have an outward orientation for our surface. Now once we have this surface S, we can use the divergence theorem, where the divergence theorem is saying that the flux across the entire surface is equal to the triple integral of the divergence inside the region that surface is bounding. Now the trick here is that this flux integral we can split into two flux integrals, where S1 is the flux across the cone and S2 is the flux across the disk. So the flux across our entire surface is the sum of these two flux integrals. But the problem only asked us to find the flux across the cone. So this is really what we want to find. This is going to be our answer. We could just compute this. This would be our answer. But if we use the divergence theorem, this triple integral alone is giving us too much. This triple integral is equal to the flux across the cone and across the disk. So what we can do is just subtract the flux across the disk from this triple integral. So the flux across the cone, which is what we want to find, is equal to the triple integral of the divergence inside this region bounded by the cone and the disk, minus the flux across the disk. So we're being a little clever here in using the divergence theorem for this flux integral. So now what's left to set these up? We need bounds for our region. Well, our region, we can get bounds for z. Z goes between the cone and the disk. Let's use cylindrical coordinates. So we know in cylindrical coordinates this cone is z equals r. We can see that again from this equation here. So z, the lower bound is the cone, so the lower bound is r, the upper bound is 4, that's where the disk is, and then we're just integrating over that disk in polar coordinates, r going from 0 to 4, theta going from 0 to 2 pi. Now since we're using cylindrical coordinates, we need to make sure that we multiply our divergence by r, because in this case dv is going to be r dr dz d theta, where these are in some order, so we can't forget to multiply by our Jacobian. What's left? We need to take the divergence of our vector field. Our vector field was xyz. So when we take the divergence, each of those partial derivatives is just 1, so our divergence is 3. It's a constant. We need to calculate the normal for this disk. We know it should be pointing straight up. We have this parameterization, so we take the partial derivatives with respect to u and v, and we cross them. I'm going to use the guess and check method. I'm just going to compute the partial derivative with respect to r crossed with the partial derivative with respect to v. So cosine v sine v 0 crossed with negative u sine v u cosine v 0. And then we'll make sure that it's pointing up. So the components of this cross product are 0, 0, and u cosine squared plus u sine squared. So really 0, 0, u. Since u is positive, This normal vector points up. That's the correct normal. Remember, if we had gotten the wrong normal, all we have to do is multiply by -1. Okay, now that's all we need to set up these two integrals. So again, the flux across the cone is equal to the triple integral of the divergence inside the region minus the flux across the disk. So our divergence was 3. We multiply by r because we're using cylindrical coordinates. Z is going from r to 4, r is going from 0 to 4, and theta goes from 0 to 2 pi. Minus the flux across the disk, so we need to compute the dot product of our vector field on the disk, which, since our vector field was x, y, and z, is going to be exactly the same as the parameterization for the disk, dotted with the normal, which was 0, 0, u. Now something interesting is happening here. If you notice, these bounds in r and theta are exactly the same as these bounds in u and v, because in both cases we're integrating over the disk of radius 4 centered at the origin. So what we can do is we can call u and v whatever we want. Why not just call u r, call v theta? If we integrate this with respect to z, then what I'm left with is a double integral with the same bounds as this double integral. I can combine them into a single integral. Now, you don't have to do this, but it's going to make the rest of our work a little bit cleaner, so I'm going to do that. So now in this step, what I've done is I've integrated 3r with respect to z, which means I just need to plug in my bounds. So I get 12r minus 3r squared. That's what I get when I integrate with respect to z. And then I've computed this dot product, which is going to be 0 plus 0 plus 4u. If I change u to r, then I'm subtracting 4r. And this is the double integral I need to compute because it has the same bounds, and I'm just replacing all the u's with r's and all the v's with thetas. This integral is separable, so I can have a single integral in theta, and I need to compute the integral of 8r minus 3r squared with respect to r. So I do that, the integral in theta just becomes 2 pi. I integrate in r to get 4r squared minus r cubed, and when I plug in 4, I get 64 minus 64, and the answer is 0. Now, some students don't like to do all this work to get an answer of 0, but 0 is a perfectly fine answer. There's absolutely nothing wrong with it. And conceptually, this makes sense. What this is saying is that there is no flux of this vector field across the cone. So let's go back up here and see why conceptually this makes sense. If we think about this vector field, x, y, z, what does this vector field look like? It consists of vectors that go straight out from the origin. So you can think that in any direction, it's a direct line from the origin. Well, that's exactly what's happening with the sides of this cone. The sides of this cone are coming straight out from the origin along a path x, y, z. Okay? So what's happening is this vector field is actually tangential to this cone. All of the vectors from this field that lie on this cone or intersect this cone are tangent to the cone. And we know that the tangents are orthogonal to the normal vector. So when we compute f dot n, we're computing orthogonal vectors on this cone. So we know that the answer should be 0 conceptually. So it's okay to get an answer of 0. It makes sense in this case. And we can use the divergence theorem in situations where at first it looked like we couldn't. Alright, so that's it for examples. What I'd like to do now is just to do a little review of some of the important concepts that we covered in Chapter 16. You can use these couple of pages of notes or this part of the video just as reference as you're going and studying for the final. We're finished going over new material at this point, but I thought it would be good just to summarize basically the more important concepts related to integration. So when we talked about line integrals, we had scalar line integrals and vector line integrals. Here's how you would set them up. The line integral of a scalar function was f ds. We had to parameterize our curve, plug it into our function, and multiply by the magnitude of the derivative of the parameterization, so the magnitude of r prime. Right? So this was the square root of the components of the derivative squared. It's not an absolute value. When we integrated vector fields over a curve, we needed a parameterization. We plugged that parameterization into our vector field, and we dotted with the derivative of that parameterization. So we didn't need magnitudes here. In both cases, we need bounds for our parameter, and that parameter went from A to B, let's say. That's what we integrated over. For surface integrals, if we were integrating a scalar function over a surface, we need a parameterization of this surface that now has two parameters, u and v. We plug that parameterization into our scalar function, and we multiply by the magnitude of the cross product of the first order partial derivatives of the parameterization r. So we take the derivatives of this parameterization with respect to u and v, we cross them, then we take a magnitude. So a little bit of work goes into computing that. For vector fields, we computed these flux integrals of f dot n on a surface, and we found these integrals by plugging a parameterization for our surface into the vector field and dotting with the normal. And remember here, the order in which we cross these matters, because it matters which direction the normal is pointing, whereas here it didn't matter because we were taking a magnitude, so the magnitude, if I reverse the order, is exactly the same. That's similar here. The direction my tangent was pointing for vector fields mattered, the way we traverse the curve matters, whereas for scalar line integrals we were taking a magnitude, so it didn't. So in both of these cases, for scalar functions, you don't have to pay as much attention to your curve or your surface, but for vector fields, the orientation of your curve or surface matters. Okay, now if we're talking about different kinds of integrals, let's talk about how you change variables in those integrals. So for double integrals, we have this area element, this dA, which in Cartesian coordinates was dx dy, but if we switch to polar coordinates, we have to multiply by r. So it was r dr d theta. For triple integrals, we have this volume element, which in Cartesian coordinates was dx dy dz. If we switched to cylindrical coordinates, we had to multiply by r, so that dv element was r dr d theta dz. And if we switched to spherical coordinates, dv was rho squared sine phi, d rho d phi d theta. So the two important things to remember here is if you switch to cylindrical, multiply your function by r. If you switch to spherical, multiply your function by rho squared sine phi. ds, this was for line integrals. We were integrating with respect to arc length, and so we just get the magnitude of r prime dt, which is what you would integrate if you wanted to find arc length. If you know what the components of this parameterization are, for instance, if you say the components of r are three functions x, y, and z, then the magnitude is just the square root of, these should be squared, pardon me, the square root of the sum of the squares of the derivatives of that parameterization. Okay. D sigma, this was your surface area element. So it was, again, as we talked about before, the magnitude of the cross product of the first order partial derivatives is your parameterization. In the special case where you could represent your surface as a function of x and y, that was the square root of the partial derivatives of that function squared plus 1. And then we generalize this to two other cases. I'm not going to write all three, but that's only in the special case where you could write them as functions of x and y. All right, what about integrating 1? What happens with all these different kinds of integrals if we integrate 1? Let's go all the way back to when you first learned to integrate. For a single integral, if you integrate 1, you just get the length of the interval that you're integrating over. A double integral, you integrate 1, you get the area of the domain that you're integrating over, some region, two-dimensional region. If you integrate 1 for a triple integral, you get the volume of the three-dimensional region you're integrating over. If you integrate 1 over a line integral, you get the arc length of that curve. If you integrate 1 in a surface integral, you get the surface area of that surface S. So integrating 1 always gives you some kind of measure of what you're integrating over. And now, the important part, the main results of chapter 16. And we'll even throw in the fundamental theorem of calculus. Right? If you integrate the derivative of a function, then you just get the function at the endpoint minus the function at the starting point of your interval. That's from Calc 1. If you have a conservative vector field and you compute the line integral of that conservative vector field, right, you're really computing the line integral of the gradient of some potential function. So it's the gradient of f dot dr, and that's equal to the value of that potential function at the endpoint of your curve minus the value of the function at the initial point of that curve. and these were independent of path, right? For these curves, all you needed were the endpoints, so I can pick any curve, any piecewise smooth curve that starts at A and stops at B. We have the first form of Green's theorem, the circulation case, where we said that the line integral of a vector field over a simple closed curve is equal to the double integral over the region enclosed by the curve of the partial derivative of the second component with respect to x minus the partial derivative of the first component with respect to y. And this was the kth component of curl. We had the flux case for Green's theorem that said the flux integral of a vector field over a simple closed curve, and both of these require positive orientation or counterclockwise orientation. In this case, the flux integral is equal to the integral of the divergence over the region enclosed by the curve. So the partial derivative of the first component with respect to x plus the partial derivative of the second component with respect to y. Then moving to 3 dimensions, we had Stokes' theorem, which said that if we had a piecewise smooth surface with a boundary curve C, and as long as the orientation of the curve matched the orientation of the surface, right, so the way you travel the curve matches the way that the normal is pointing, then the line integral of the vector field over the curve is equal to the flux of the curl across the surface. And then we had the divergence theorem, which said we needed a closed surface, so some surface that encloses a 3-dimensional region. Then the flux of a vector field across that surface is equal to the divergence, the triple integral of the divergence inside that region. Okay? And so all of these are some form of the fundamental theorem of calculus. And in what way? In each of these equations, in each of these relationships, we're integrating some type of derivative, and we can represent that as the values of the function on the boundary of where we're integrating the derivative. So here it's straightforward, right? We integrate a derivative, we get the value of the function on the boundary at the endpoints of the interval. Here as well, we're integrating a gradient, which is a form of a derivative. We get the values of that function at the endpoints of the curve. Here, now I'm switching my derivatives and boundaries, but here I'm integrating a relationship of derivatives. It's equal to the integral of the value of the function along the boundary of that region. Here's another form of derivative. It's equal to the value of the function integrated over a curve. Here it's the flux of the function itself, and these are the derivatives of the components of that vector field. And then here are those same things just in 3 dimensions. In this case, my region is a surface bounded by a curve, so I have derivatives of f, in this case it's the curl of f, equal to the integral of f on the boundary of that curve. Here I have some 3-dimensional region, and my derivative is the divergence, and that's equal to the value of the vector field on the boundary of that region, which is a surface. And that's it for Calc 3. It's been an interesting semester. Certainly we ran into some things we didn't expect. Good luck on the final, and happy studying.